So let's go over some of the concepts in chapter 3. And as I said in class, that this again is covering some fundamentals, and many of them we will come back and talk about in more detail later in the semester, but it's also building on what we were just talking about in chapter 2 in terms of discovery of the atom. All right. Now, so the important thing to understand here is that a lot of the understanding of the atomic structure came from the behavior of elements and compounds in electric fields. And in a lot of that, things would happen when we've seen things like, in this case, static electricity. We know it happens, but we don't really understand it at first. But basically what you have to understand on a fundamental level is that when one object is going to lose electrons, something else is going to gain them. And you'll see later on that that's the whole premise of batteries and all of this kind of thing that we'll talk about. And I'm just going to introduce that here with the electrochemical cell, okay? So here you can see what we experienced already when we were kids, especially on a really dry day. The electrons from our hair can be transferred to the environment, or in this case to a comb, and that's just static electricity. So you can see the movement of these electrons as they're trying to get off our hair. All right. So a lot of these experiments also grew out of the behavior of currents. And some of these already as early as the 1800s. So Alessandro Volta, he was looking at electrochemical cells. And indeed, we're going to have a whole chapter just on these different types of cells. But suffice to say that already then they knew about electricity, even though we didn't have light bulbs and that kind of thing yet. We weren't doing that yet. As you know, things didn't become electrified until the late 1800s, early 1900s, when we were actually getting electricity put into homes. But playing with electric fields was already taking place. And that was going on in tandem with our learning of the atom and accepting that and what it does. So if you look at an electrochemical cell, they knew that there would be some sort of source of electricity, okay? And that they could funnel that through some sort of a container that could contain what we call an electrolyte. So the electrolyte would be very often salt dissolved in some sort of water, but it could be also molten. And it's going to conduct electricity. And that electricity is going to move between electrodes. So it could be metal strips, or in many cases, carbon rods. And there would be some sort of a current that could be measured in this process, all right? They could see this happening. Now with this, when we talk about this, and we're going to go over this again, the part of the electrochemical cell that's positively charged is the anode, and it's attracting the anions, which are negatively charged, which we now know are electrons. And from the other side, the cathode, all right, that's the negative electrode, and that's attracting the positively charged cations, okay? So in both cases, we're having the transfer of charge, all right? So learning about electricity came along in parallel with our understanding of the atom, all right? So there's sort of both of these things were going on at the same time, and they were working together, as it turns out, historically. Okay, so in the understanding of electricity, there was this thing called a cathode ray tube, or a Crookes tube. Crookes tube had a screen coated with zinc sulfide on it, and this would be a vacuum. All right, so there wouldn't be any gas in here. And what they saw was that when they applied an electric current to this tube, they would be able to see light coming off of this screen, all right? But they knew that this wasn't light per se, okay? So they didn't understand yet about this. It was a green fluorescence that was coming off of this, and we'll talk about fluorescence a little bit in a bit. So what was happening is that as the electrons were traveling through this tube, all right, so they could see that this seemed to grow out, this ray seemed to grow out from the cathode toward the anode. So they knew that it was a negatively charged particle and of some kind. So they knew that there had to be something negatively charged in these atoms. And if they would put this in a magnet or a magnetic field, it would be deflected away from the negative plate and towards a positive plate, or towards the positive side of a magnet and away from a negative. So they knew that there was some sort of particle in this beam, and Thomson, who is known for doing this experiment, called these things electrons. So they knew that they had a negative charge. And that caused, and indeed what we looked at how this works on this video here, all right? And he was trying to work out the idea of what would be the mass of this particle. So he was trying to lead to this understanding of a mass to charge ratio, which I'm going to come back to in a sec, all right? Now, while this was taking place, another scientist named Goldstein was trying to find out, is there any positive nature to this electric current? So his way of doing this would be to put holes in the cathode and then be able to detect the positive charge coming the other direction, so away from the negative plate. Because they would be repelled from that, so they'd be traveling towards away from the positive plate and going towards the negative plate, all right? So, and by putting holes in the cathode, he was able to detect that, all right? So, and that, again, they were looking at the mass to charge ratio, and Goldstein actually worked out that the mass was a certain value, and you can see that in my notes, okay? But then they assigned that on basic units, a 1 positive charge. Okay, so I'm going to talk a little bit about that now when we talk about the Millikan experiment. So what Millikan was trying to do is actually figure out the charge on a what the charge was on an electron, because here, if you look at the Thomson experiment, we knew that there must have been a negative charge, but we don't know how many and how much that was, and how much mass would be assigned to that particle. So this comes to this idea of the mass to charge ratio. So how the Millikan experiment worked, and I sort of showed you this one video on that. This one over here goes a little bit more into the math, and it works it out actually for the degree of positive charge to it, which sounds a little counterintuitive, but that was before they would, ionize these. So there was a set of experiments that was done, right? So the original experiments, what was done is that they would take an atomizer, which is basically like a perfume bottle. So you're getting tiny drops, okay, of oil. And instead of being perfume, it's oil. And some of these would pass through a plate, and then they would, and they could see the mass of that drop based upon how quickly, by gravity, it would reach the bottom of the experiment, okay? So then they could assign a mass to a certain size, not a mass, a velocity to a certain size particle of oil when it fell down towards the bottom plate due to gravity. Then what was happening is that when these particles of oil passed through this plate, they would actually interact a little bit with the plate, and some of their negative charge would be stripped away. So there would be a degree of negativity to the charge or a degree of positivity to the charge versus the size of the droplet. So what they ended up starting to do then is that they would add in a source of ionizing radiation, and this would give these particles a negative charge. So they had the size of a particle, a certain amount of negative charge, and then what would happen is that they began to apply an electric field here. So they had a negatively charged plate and a positively charged plate, and an electron or a negative charge is going to be repelled away from the negative side and be attracted to the positive. but at the same time, the mass of this drop is going to be being pulled down due to gravity. Okay, so in this experiment, they would now charge up these particles with negativity, and once they had a certain balance between the charge and the force of gravity, so there'd be an electric charge, an electric force versus a gravitational force, and they could actually freeze that particle in this device and actually look at it through a scope, okay, or a microscope or telescope here, and actually see that particle floating essentially in the balanced force of gravity versus charge. So they could get a certain amount of understanding of the mass based upon the acceleration in this case, as well as then how much charge, because they could regulate the amount of charge here on these plates with a dial, okay, because you could regulate the charge, and how much charge would be needed to balance this out, okay? This sounds really complicated, but it's really quite elegant. If you want to see how it's done in a little bit better, you can watch this video, but just forewarned, then in this case, this one is talking about before they actually charged up these particles, and they were working with particles that had lost some of their negativity, so there was a different degree of positivity in this, and these two plates are flipped the other direction. So the positive plate is down here and the negative plate up there, okay? But here now, at this point later on in their work, they actually charged up the particles and gave them a negative charge, so they knew exactly what they were dealing with instead of degrees or more or less negative, all right? So here they would charge up ththese particles. But basically, it's the same idea. They would have an understanding of the mass of this particle, or how, not the mass, but the amount of charge that was applied to these plates, and they could then use equations to figure out the charge of the particle, or how many negative charges or decreased positive charges, if you look at it before they ionized it, and could relate that to the charge of the electron. Okay, and they basically found that the amount of electric voltage that would be applied here in order to get these particles to float, essentially, were in certain small number units, and they were able then to work out how many electrons there would be, because the very minimum one, that they couldn't get any smaller or any less charge to get this balance, what they then determined would be 1 electron, and you can see that what the charge of that electron was, and from that they could also then work out the mass, okay, because they knew how many electrons they had for a certain amount of mass. So then they developed the mass of the electron. All right, this was based on the charge to mass ratio, okay, which was already an idea that was introduced back here by Thomson. Right, so it's really quite an elegant experiment. Quite complicated, but very powerful. And as you can see here, they had spent years on perfecting this. So you can, if you're interested, you can watch this. And this one sort of shows you how it was done. Okay. Now, so what they ended up determining was that for 1 electron, right, they assigned that charge for 1 electron as -1. So they had given that charge, and then they also determined that the actual mass of that electron was very small. So if they saw 2 units of that charge, they would say 2 electrons. So when we're dealing with the charge of an electron, we're not actually looking at the actual charge, as you can see in the video. It's like, something really actually very small, because electrons are small, but we assign it a -1 or a -2 if it's 2 electrons, okay? Just to make our math easier with the understanding, again, sort of like the idea of the mole, right? We know that when we have 1 mole, it's actually, a large number of atoms or molecules, all right? So here, even though we're dealing with a charge of -1, we know it's actually what the actual charge is, okay? And they were also then, of course, able then to derive from that charge to mass ratio the mass of an actual electron, which is incredibly small, okay? In my notes, I have 9.1 times 10 to the negative 28 grams. So it's very, very small. Okay. Now, with this, and while they were doing all of this work, and they're putting these electrons and these substances in electric fields, they were able then to see that there was some sort of energy being given off. Okay. Now, the first example that I showed you here was with this zinc-coated plate. And if you know anything about zinc, you know zinc has that sort of green sort of color. And we're going to do a lab on this. You can see the colors that are given off, and we'll talk about that a bit more later. But they could already see that there was some sort of energy being given off, right? Because this was in a vacuum. Now, with that, one of these scientists that was studying this was Röntgen, and he was able to see that some of this energy that was being given off, he couldn't see it, but he was able to detect it on a screen, a very sensitive screen, all right? It's chemically treated paper. And he was able to see that it could actually get out of containers. And since he didn't know what this light was called, or what this, this energy was called, he gave it the name X-rays, all right? And he was looking at the behavior of all these metals. As you saw, zinc was producing a color green in these electric fields. So this is where he sort of accidentally determined this just by what was in his lab. All right, he actually could see that other experiments, it could actually go through walls. And the famous picture here, this is actually his wife's hand. So certain things these X-rays could get through, and other things it could not. So it wouldn't be able to get through bone, for example, which is why you have a darkening on the screen in the places where there was something that was dense enough to stop these rays. All right. Now, in the other side, with Thomson's experiment, where we're talking about this green light, right? Green light. So that we called fluorescence. Now here, what's being given off very often when we're looking at this is a color of some kind, so sort of visible wavelength of light. And then we'll talk about how this works in a few slides. Most of the original work was done using light that we could see. So very often when we're talking about fluorescence, we sort of think about visible light being given off from some sort of a reaction. Okay, but now with the science as it's progressed, a lot of the fluorescence light is other ends of the spectrum, even outside of the visible. All right, so ultraviolet and infrared. All right, you've probably heard of that, but that's sort of one more violet over from the violet, and infrared is one more red over from visible red. So, but of course, there's a continuum of wavelengths that span this region, as we'll get into in a little bit. But basically, the understanding that chemicals can glow or give off light, in the work being done with that, led to the sort of accidental discovery of radioactivity. Now, the difference with something that's radioactive versus something like a substance that will give off X-rays when energy is applied or voltage is applied, or give off visible light when a voltage is applied, is that elements that are radioactive will give off this energy on their own. They don't need an energy input. They already have enough energy inside of them that they can emit this energy on their own. Okay, so that's sort of what we're going with here. And Becquerel was the scientist who determined that this was the case. He was working with certain chemicals that would produce fluorescence, or that was on the order of X-rays, so it was powerful, it could get through things, but they didn't need to be exposed to light or to electricity beforehand. They would just emit these things on their own. And Becquerel's graduate student was Marie Curie, okay? And this was before she was married. So you can see her maiden name here, Sklodowska, something like that, Sklodowska. That was her original name. It's not as easy to say. It doesn't roll off the tongue as easy as Curie for someone who's mainly English speaker like me. But she was the one that coined the idea of, or the term of, radioactivity. So she kept experimenting with these substances throughout her life, as you know, and she actually has 2 Nobel Prizes. So she kept working on this, and later on her husband joined her, all right, so Pierre Curie, so they also shared a Nobel Prize, and working on these compounds, all right. So here, again, these are types of chemicals that can emit light without any input from, or emit radiation of some kind without an input of light or electricity, okay. And certain substances, like you probably know uranium, but the Curies were working with polonium and radium, okay. And of course, I don't know if you know this, but eventually Marie Curie died of her experiments because she didn't realize that it was damaging her tissues. So, and then her daughter also started experimenting, and her daughter also was a Nobel Prize. So basically, who came later, Rutherford, he was considered that there was 3 different types of electromagnetic radiation, all right? And Rutherford was naming these particles and or these types of radiations. And when he called them were alpha, which is this guy here, gamma, and beta, all right? And a series of experiments was needed to sort of determine these different types of electromagnetic radiation. Okay, so as you can see, radioactive substances produce their energy spontaneously. The Curies identified polonium and radium as 2 of those, and later on we learned about uranium. So if we look at the different types of electromagnetic radiation, they have certain particles, and they are penetrating to certain degrees depending on the amount of energy in the particle. So alpha radiation, this is a positively charged type of radioactivity. It has a certain amount of mass associated with it. All right, so later on we're going to do some, work with some of these things when we do the radioactivity chapter to know what kinds of radiation you're getting and what it does to the particles it interacts with. But here you can see it has a mass of 4 units, so 4 atomic mass units. So and a charge, okay, of +2. All right, so it has a charge twice that of an electron. All right, so it's a positive charge, so it's double that. Okay, because a positive proton has the opposite charge of an electron. Now, beta, on the other hand, is a negatively charged particle, and it has the mass of an electron. So, and so it's a fraction of that charge of a proton, and it has been assigned a charge of -1. So that would be the beta particle. So that's a negatively charged. It's considered an electron. And it has much more energy than a typical electron. So a beta wave or a beta particle is more energy than a regular electron, but it's called a negatively charged particle, and it has the mass of an electron. Okay. Now, on the other hand, gamma waves, they don't have mass and they don't have charge, but they're extremely penetrating. All right. So no charge, much more energetic than X-rays. All right. So as you'll see, as we watch in this video, we're looking at the whole spectrum of electromagnetic radiation. And you can see the difference in the wavelength. So the longer the wavelength, the less the energy. The shorter the wavelength, the more the energy. So gamma waves have a very short wavelength, very penetrating because it can easily get through materials. And in order to block these, and we're going to do this later in the semester, but alpha particles can be blocked with a piece of paper, whereas gamma rays, you need to use lead, all right? So again, alpha particles are considered positive. Okay, so it's basically the nucleus of a helium atom, right? So we've got, that's sort of the mass of this. So considered like helium atoms. Beta particles are negatively charged with the mass of an electron. It's considered to be an electron. So alpha particles are considered a helium. Beta particles are considered electrons. Gamma particles don't have mass, but lots and lots of energy. All right. Okay. Now, how are these particles determined? So there's a lot of really elegant experiments that were done here, and how they were used to determine the structure of the atom. And that was sort of the important thing here, because now when we're dealing with radioactive waves, these things are small so that they can influence an atom. And that's how we got to the structure of the atom. So Rutherford was doing these, playing with these different types of experiments and helping us understand the nature of the atom. So one of his first experiments was this idea of bombarding gold foil with an alpha source. All right, so here we know that this is a positively charged ray. Okay, and when he saw it penetrating through this gold foil, okay, so this was very thin, so it could get through. He saw some of them, a lot of it get through, but some of them were deflected, all right? So this he had used then to surmise that the atoms, or of the element gold, must have some sort of positive part, but it was very small, because not all of the alpha particles were deflected, all right? But somewhere. So he said there must be a positive core to the atom that would then repel the positively charged alpha particles. All right. So that was done with the gold foil experiment, which you can see here. So here's his alpha source. We know that these are little helium atoms that are coming through here, right? And it's positively charged. And what's happening here is that if they would interact with the nucleus of a gold atom, they would be deflected, all right? And he saw that some of these would be deflected, and because they weren't following through on the path, it would hit this, as you can see here, they've got this zinc sulfide screen. Again, remember, it would light up, okay, just like it did in the cathode ray tube, or the Crookes tube. And he would be able to see that light up. In some places, it would light up in weird locations. So he surmised then that the core of the atom was positive and was very small. Okay. Whereas the rest of the atom must have a lot of space, because these positive charges could easily get through. And they already knew that there must be some negativity as well, but these alpha particles didn't seem to be affected by that negativity, in which case they would bond to, right? But then they also knew that these positive charges in an atom were much heavier than that of the electrons. So there's a little bit of putting these different experiments together. Okay, all right. So, like I said, the electrons then had such little mass that even though they had a negative charge, they wouldn't really be affected by these alpha particles, all right? And these alpha particles could easily pass through most of the substance of the atoms in the gold, all right? So that then left this idea that we have positive particles, right, or protons that have a charge equal in magnitude, but opposite that of electron, in a mass the same as a hydrogen atom, okay? Looking at all of this work, because looking at the charge to mass ratio and all of these other things, and now working on protons. But what they observed, though, is that atoms were heavier than the number of protons, okay? So remember, we were dealing with the helium atom idea, that the alpha wave was essentially a helium atom, and it was positively charged, but helium was found to have a mass that was double what was observed for the actual mass of the protons that were available in the helium. So this led him to hypothesize that there must be a neutrally charged particle also within the atom. and he charged his graduate student to, I think it was his graduate student, to try and figure out an experiment that could figure that out, okay? And this was quite elegant as well. So what he did, so what Chadwick did, and not that you're going to have to be able to get all of these different ideas here, but again, there was a Nobel Prize that was awarded here. Look at the timing that we have in the 1930s. And this is going to come right down to our talk about radiation later on, okay? So here what they used was a polonium source, was giving off alpha radiation. So we know that that's positive. And it would hit beryllium. And then there would be a charge put across here to try and get rid of any positive or negative charge. But he was able to figure out that there was also a neutral charge, because what was happening is that even though they couldn't detect the charge here, because he would eliminate the positive and negative charges by putting plates here, these neutrons would hit paraffin, all right? So a paraffin strip, and then that would give off radiation. So it would give off protons, and they could be detected by a Geiger counter that could measure the radiation or the charge that was given off from the paraffin as a result of some sort of particle hitting it from the alpha source, which first hit the beryllium. So then he suggested the only way that this could have been done is through a neutral particle. And again, they worked out the charge to mass ratio, and they got to this idea that the neutrons were about the same mass as a proton. Okay, so you can see there's a very interesting set of experiments here, based and very elegant in order to be able to detect all of these different effects. Okay, so, and that's all based on this idea of radioactivity. Okay. Okay, so now remember, alpha particles are positively charged, considered a nucleus of a helium atom. Beta particles are negatively charged, very small mass, all right, so they're considered electrons. And gamma particles, gamma rays, no particle there, it's just energy. So no mass and no charge, all right, but very, very powerful energy. Okay, so where did that leave us? So you can see some of the work that was done, some of the elegant experiments that were done, and obviously there was math and a lot of different types of experiments that went into that. Since I'm just showing you the take-home message experiments, all right? So they built, scientific method here. So they had developed a certain level of understanding. So now where are we at? So we understand now that the atom is composed of a nucleus, which, as you can see from the experiments, okay, very, very highly dense nucleus, all right? So that was coined by Rutherford in his gold foil experiment. And in that nucleus, we have the positive charge, and as well as our neutral charge, so our neutrons. Okay, so in the nucleus, we have our protons and neutrons, and on the outside is where we have our negative charge, these really tiny particles, where we have our negative charge, so those are our electrons, and those electrons are found in these shells, which we're going to talk about where we get these shells from. Okay, so when we look at this, when we have a proton, we assign that now, regardless of its mass, a positive charge. All right, so they worked out charge to mass ratio, positive charge. It's considered to have a mass of 1 unit, okay? And the neutron is considered to have an equal mass, but of course no charge. The electron is, its mass is only a very small fraction of that of the proton, all right? But we've assigned it, as I described, a negative charge, and we know that's outside the nucleus. So when we talk about the atomic number, that is how Mendeleev originally organized his periodic table, right? Increasing atomic number. We now know that that atomic number is the number of the protons, right? So if we talk about the helium nucleus being given off in an alpha ray, we say that, that is a proton nucleus. So it has a mass, right, of 4, even though it has a positive charge, because remember, we also have our neutrons. Okay, so that's down here, so our mass number. So our atomic number, as I said, is the number of protons, but the actual mass is that with the protons and the neutrons. So that would be our atomic mass, or our mass number. So if we're looking at helium, the mass is 4 and the atomic number is 2. All right, and that was giving Rutherford that idea as well. We have a charge that was a mass that was double that of that assigned to the protons, so we knew that there had to be something there, and that was the neutrons. Okay. Now, with that though, so now we go back to Dalton's theory that we talked about in chapter 2. So remember, the part where Dalton got his atomic theory a little wrong was that he said that every atom of an element is always the same. What he missed out on is that atoms of different elements can have different numbers of neutrons. So every element will always, always, always have the same number of protons. That is why the periodic table works, right? So we have it arranged by, at first by Mendeleev in order number of protons, which was, fortuitous. But the isotopes, on the other hand, so the full mass, will cause different elements to have slightly different, certain elements to have more than one mass. So when you look at the periodic table, you'll see the atomic mass might have a decimal place with it. So what they do is they take the incidence of these different isotopes and they calculate an average, all right, an average mass based upon how frequent that the different isotopes are found, all right? So when you talk about hydrogen, for example, it's just a little bit different than 1 because these other 2 isotopes are less frequent, so it's going to be closer to this 1. So here we have deuterium and tritium, whereas carbon, we use, I think, carbon 12, but if you look at the periodic table, it's 12.0 something. So there's also these other isotopes, 13 and 14, right? And 14 is the one that's used for carbon dating. So now these isotopes, how do they determine them? Well, because they give off energy, all right? Sometimes the isotopes give off dangerous energy, like gamma rays, but other times not, okay? And that goes back to our idea of radioactivity. So there's isotopes, and then there's radioisotopes. So radioisotopes will give off alpha, beta, or gamma rays, okay? And sometimes it of X-rays. So, so this comes from dating fossils, all right? So here we get the carbon-14, but we also use radioisotopes in diagnostic imaging in medicine, cancer treatments, and power supplies for pacemakers. So that energy can be used in very useful ways. So I don't want you to think that all radiation, radioactivity is bad, all right? So there's different ways of harnessing that energy, all right? Okay, and the reason they give off that energy is because the radioisotopes are unstable, all right? So they're going to decay, all right? And this is something we'll talk about later. Now, where are the electrons? So that was the other thing. So another thing that they observed when they were looking at metals was that they would give off certain colors, all right? And this is what we're going to do in lab. We have one of these instruments. This is a flame atomic absorption spectrometer. That's what you're looking at here. It's not fully assembled. We've inherited it from another lab, but I was hoping it would be together, but it's not yet together. And if future students are using this video and it is together, you can see that eventually, at one point it wasn't put together when I was teaching this course. So what's happening here is that certain elements, when exposed to flame or when they're combusted, they give off certain colors. And the reason is because the electrons are located in certain positions. Okay, so you could also think about this as in terms of fluorescence as well. So they're giving off energy, and you can see that as light. Okay, so whether the energy input is from electricity or from radiation or from heat, you're going to see packets of energy given off in different ways. And here we can see it given off as light. okay? And each wavelength of light has a particular amount of energy, right? As you saw in that video, when they were separating the spectrum, they looked at the temperature of the different colors of light and realized that they were different. It's because they're giving off different amounts of energy. Now, this property can be used to look at what types of substances or metals are present within a sample. And I actually used to do this back when I was an undergraduate, way back in the late 80s. I worked as an analytical chemist, and I worked on flame atomic absorption. And basically, I would have my sample in a fluid, and I would ignite it in a flame. And the elements then would produce certain colors that could be detected on a screen, all right? And what you get are these line spectra, okay? And so every element has certain emission lines. So here's a continuous spectrum. This would be in the visible range. And you see cadmium has very particular lines of energy that would be emitted from when it's ignited. Okay, so a continuous spectrum would be, you can see all of the wavelength, and a line spectra, very specific packets of energy that are being released. So when it came to looking at the model of the atom, we had this idea of the Bohr model, we had, and these spheres, and and then with other understanding, we knew that electrons were the outside, and a lot of this became put together. And oh, this is the one thing that's in my notes that I didn't mention here. Fireworks are based on this premise as well. So you have certain colors in the fireworks, and they have certain elements in them to give off those colors when they're ignited, right? So if you look here, right, so we know in visible light, when it's passed through a prism, you can actually separate those spectral or emission lines. And like I said here, certain elements will give off certain packets of color when ignited. So this caused people to think, well, why is it only certain amounts and not continuous when certain elements are heated to give off these line spectra? So this had got scientists to think that, well, there could only be certain specific amounts of energy, or quantized, or packets of energy that could be released as certain frequencies. All right. So what a quantum is then is that there are specific frequencies of energy that can be absorbed and then emitted. So the electrons then are spaced around the nucleus in certain places and not in between, because we don't get, you can get very specific wavelengths of light that are produced. And this is also the principle of fluorescence. So what's being done is that energy is being put in the form of heat or electricity or whatever it is, and the electrons then are excited. They move to a larger sort of quantum or level, okay, to absorb that energy. And then when, so this we call the excited state. And then when the source of input energy is removed, the electrons drop back down and they emit light as well, okay? So what this would then call then are energy levels, okay? And the one that's at the very bottom then would be the ground state, so where it actually, the electron would normally reside. And the excited state would be when you've got the energy input, and when the energy is released, it's given off as a photon or a wavelength of light, right? So the electron can't reside anywhere in between these spaces, okay? So looking at the Bohr model, this is what we're looking at now, all right? So this is a scientist named Bohr. He worked this idea out, and I think, no, I just introduced it here. So the Bohr model, okay? So he's got these certain packets of energy. The electrons are existing in these sort of orbitals or shells around that nucleus. And Bohr was saying that each shell can only hold a certain number of electrons, okay? Now, what's going to happen then, so here we have our electron in the ground state and we get hit by a charged particle, so radiation or heat or something, and it's going to push that electron up into an excited state, and then it will drop down, giving off light, okay? And the certain distances can give off certain types of light. So we can give off ultraviolet, we can give off infrared, we can give off visible wavelengths. And the distance between these different orbitals is responsible for the amount of energy that is then given off in that wavelength. All right. Okay, so now, as I said, the electrons can only exist in those particular places. All right. And this is where we start thinking about this weird idea that electrons are particles, as we've been talking about. We could see that they have a certain amount of mass, so they must be particles, but they can also exist as waves. And that was the way they were able to sort of wrap their minds around the fact that these electrons could only exist in certain places, all right? And so I'm going to get into that as we move forward here. So now going back to the Bohr model, all right? So we know that, say, hydrogen, it's got one electron, and it has one proton and therefore one neutron. All right, so if we're talking about the main isotope of hydrogen, helium has 2 protons and balanced out with 2 electrons, 2 neutrons. So, as we go through, what they determined with the Bohr model, the number of electrons that must be existing outside of that element, outside the nucleus of that element, and the way they figured out how many electrons there were is that it followed this nice formula. Okay, so if you're talking about N would be the shell number, right? So we're talking about more and more layers or shells around that. And this is how you can figure out how many electrons are found within that shell. Okay, so that's the basic idea. So if we look here in the first row of the periodic table, we have the first shell. Okay, and remember, we're coming at this after Mendeleev developed this, all right? So this is why it's just incredible. So here in the first shell, we determined that there was two electrons, and then when we get into the second shell, all right, it worked out that there's a total of 10 electrons, all right? But we already know that 2 are in the first shell, so a full outer shell here would have 8 electrons. And this is where we come to this idea of the octet rule, and we'll talk a little bit more about that when we talk about bonding, all right? And then the third shell, all right, we can have a maximum of 18 electrons in the third shell, all right? So this is how they figured this out, and as you move up through the periodic table, you're gaining one more electron as you're going across the lane, all right? Now, so the electrons, all right, they're going to be filled with a certain pattern into these energy levels. So the energy level itself, all right, so what that is the distance from the nucleus. And then the sublevels are then going to accommodate those electrons, all right, so it's going to be a certain amount in each sublevel. And then the orbitals is where they're actually sitting, or they're most likely to be found. All right, so if we look at this, so here we have this quantum model, quantized energy. We have electrons in their ground state, are most likely to be this, and notice it looks kind of fuzzy. And then in the excited state, you can see that drifts outwards. So some of those electrons are going to move out into the other energy levels, and then they're going to start dropping down, okay? Now, the way it worked out is that they assigned the first energy level an S, and if you look at it, notice it's sort of spherical. And then the second energy level includes an S, but it also includes this new orbital called a P, so you can see it has sort of a dumbbell shape in terms of the probability of where you'd find these different electrons. So this is pretty weird, right? Because look at the shape of this. So how does that work if we're dealing with a particle? And this comes back to the idea that these are also waves, all right? Now, then the other thing that they started coining is these different sublevels. So I'm getting ahead of myself here. So let's go through these slides. So we have our principal energy levels, so our shells, all right? And they're going to correlate with the distance out from the nucleus, all right? So, so if we're dealing with neon, for example, we have 2 shells, all right? So if we go back Look at this periodic table. So now here we're in the second shell, in the second row. Again, remember Mendeleev did not know anything about this yet. So we're in the second row. We've got two different kinds of shells. And in that we have S and we have P. All right. But we also have the first shell, which is another S. Okay. So here the principal levels, the shells are how far they are out. And then the sublevels, all right, so each energy level is going to be divided into the number of that energy level sublevels. So if we're dealing with the second, we have two energy levels in the second one, or the second, we've got two sublevels in the second shell. And then within that, where are those electrons actually found? Well, they're found in particular orbitals. So here we have one s orbital and three p orbitals to accommodate the other electrons. Okay. Now, if we look at them separate, you can sort of see the s orbital and the p's all sort of superimpose upon each other. Now, the next idea was that how is it that they can exist only in these places but not others? Because these things are particles. They should just be able to spin around. And this is where it came to the idea of de Broglie. His idea was that these electrons are going to behave as both particles and waves. Now, something you've probably noticed, and we showed these, this video of standing waves, right? So if a particle is moving, and remember these are moving really, really quickly. So the way they figured out that it must also be behaving as a wave is because if this particle was moving quickly enough, it would catch up with its own energy and it would destroy itself, right? So this would be the idea of a standing wave. So basically what you're looking at here is an electron in a standing wave, all right? You can sort of see it going around, and anything off of that standing wave, so any wavelength that would be or a little bit different than that would destroy the position of the electron. So in that regard, you could only have those electrons in certain places, because if they were outside of those orbitals, the standing wave would be destroyed. So if you think about it, when you're looking at, say, a pond, and you've no doubt done this, it's a very still pond, you throw one rock in, you can see all the waves radiating out from that. But if you throw in another rock, the competing waves will cancel out some of the first waves. And other ones will get bigger because they'll amplify themselves, right? And eventually, in that system, it degrades down, but here it doesn't. All right, you've got this energy constantly moving forward, so you have essentially a standing wave. You actually see the difference. And in the one video that we looked at, we were looking at, they showed the guitar string in terms of, the way the string is vibrating depending on where you're putting your fingers. So you could sort of imagine that as sort of a way of visualizing a standing wave, all right? Okay, so I know that's kind of weird to think about that, but that's how it worked. And then a lot of experiments were done in order to show that these particles also behave as waves, okay? And we showed some of these videos in class so you could sort of visualize this, because I know it's kind of a weird way of imagining things. So then in terms of how we fill these orbitals, so it's pretty easy at the beginning, right? So in the first row of the periodic table, we have one energy level, so we have the 1s, and then we will start filling electrons into the 2s, and then the 2p, and then to the third level, we start into the 3s orbital, and then we go into the 3p, and then to the next level of the periodic table, we start filling into the 4s. Notice that happens before we do the third shell around the third level, which is the 3D. We're not going to get to that point, but there was a methodical, and it works really well, methodical way of adding electrons to these, okay? And what you'll see here is that you'll see, if you see this kind of thing, you can see, okay, lithium, there's one electron in the outermost shell, and this is actually called the valence shell. So the outermost shell in which we have electrons is called the valence shell, and that is the one, depending on how well it's filled, will determine the chemical activity of that element, and we'll talk about that aspect a little bit later in the semester when we talk about different types of bonding and how that works, okay? But we'll, hang on to that thought. So the chemical behavior of the atom is determined by the electrons in the outermost shell or orbital, and that's called the valence shell. And in a chemical reaction, these electrons can be gained, lost, or shared. And we're going to go over that in detail later on in the semester. Okay? Then, harkening back to the periodic table, all right, so far I just sort of told you how that came, where that came from. So the rows are called periods, okay? And as you go through the rows, there's going to be a range of metallic or non-metallic properties, conductivity, depending on the directionality and in which way you go through the periodic table. And that's how Mendeleev was able to predict densities and behaviors of his different, of the different elements, even though they weren't discovered or made yet. Whereas groups, these are the vertical columns, all right? And the chemical behavior of these is going to be very similar because their outermost shell is going to contain the same number of valence electrons. And again, we'll talk more about that later in the semester. All right, so here you can see some of the ways of looking at this. So atomic radius, you can see the differences here. See these ones, the radius is getting bigger, here it's smaller. Melting point, you can see certain patterns here. Ionization energy and electronegativity. All right, so non-metallic character, metallic character. You're not going to have to memorize these, but you need to understand that the periodic table can be used to predict some of these ideas, okay? Now, the last thing that we brought in here was the aspect of green chemistry that's put forward in this chapter of the book. And here we're talking about trying to gain clean energy, renewable energy from solar fuels. And I think the figure is that we get enough energy from the sun in 1 hour to supply the entire planet, all of our activities for a year. So you can see how much energy we're getting from the sun. And the idea here is to take that energy and convert it into some sort of storable fuel, right? So we have solar panels that can use that energy and converts it to electricity directly. But ultimately, for this to be most useful is that it can be harnessed to create a renewable fuel that we could then use to power our devices, even when it's not sunny out, right? In different ways. So it's much more convenient than driving around with giant solar panels on your car, all right? So there's two main ideas to consider here, and there's a lot of work being done here, which is why, of course, we have programs on campus that just are looking at this very idea. But the two main ideas, all right, the way I'd like to frame them and the way your book is framing them is first, using the energy from sunlight to split water to generate hydrogen and oxygen, and then using hydrogen, or H2, not the elemental hydrogen, but the gas, H2, as a fuel, all right? So converting it to a liquid fuel, for example, under pressure. That is one idea. So right now, this is a very expensive process, all right? Then the other idea is to mimic photosynthesis. Plants have been doing this since there have been plants, right? So they take energy from sunlight, okay, and they then take CO2 and water and convert that to a carbohydrate, which we like to eat, right? Why do we eat it? Because it's got chock full of energy and give off oxygen, all right? So the idea here is to do the same thing. Take CO2, right? Now we've got plenty of it in the atmosphere, right? And sort of then make sort of like an artificial leaf, or use specially engineered plants like algae to help us harness that and convert that as well to a fuel. So instead of being like carbohydrates as in fuel, as in food, strings of carbon to then be used to be a liquid fuel to then power our devices or our cars. Now, the key thing, and when we watch a couple of these videos, right, so this goes back to our idea of a catalyst. Now, the way plants do this, right, they've got chlorophyll, right? That's why they're green, or some sort of pigment that helps them do this. And and coming back to what I was saying before, catalysts, okay? Remember, our biological catalysts that help our chemistry take place in our body are called enzymes. Now, you'll see that when they're talking about these techniques that they're talking about in these videos, catalysts, right? And very often these catalysts, as I had mentioned earlier in the semester, are expensive or precious minerals or elements, all right? And the idea here about green chemistry is to move away from that, to find catalysts, so again, to help this take place. Remember, plants have catalysts to mediate this. So now we're trying to then take this, and here we're trying to do a chemical reaction, right? So we want to split water. That's going to take energy. So we have to try and lower the energy input by using a catalyst to do this. So instead of then using these precious metals, can we create something like an enzyme or an artificial enzyme to mediate this, or use a different structure, say for an element that's more common, such as iron on our planet, to mediate this, so that this can be a cost-effective alternative to digging out or pumping out fuels from the ground, which is not sustainable. Eventually we're going to run out of it, and even the ones that we do have are getting harder and harder to get at. Okay, so the idea then is to make this cost effective. And you know, we watched a few of these videos in class to show the kinds of things that are being done here. All right, so but remember, the take-home message here is that we're trying to split water, get hydrogen as a fuel, or sort of mimic photosynthesis and generate some sort of carbon chain, all right, and probably as a product, oxygen. All right, so that's those are the two tactics that are being followed, and we'll talk more about those over the course of the semester. All right. Okay, so that's it for this chapter. So hopefully this review has been helpful. I know some of these concepts are quite complicated, but remember, when in doubt, you fall back on the study guide and the homework so that you can appreciate what we're expecting. All right? All right, thanks.